Hello everyone, I hope you're having a great weekend. This lecture will replace not having class this coming Tuesday. Tuesday is Veterans Day, but we're getting toward the end of the semester and we still have quite a bit of material to cover, so I appreciate you taking the time to watch and listen. So what we're going to do is we're not quite done with Chapter 9. Chapter 9 focuses mostly on the Lewis model. But we're going to start moving into Chapter 10 because we're going to look at a new bonding model that builds off the Lewis model. Okay? So far we know how to draw Lewis structures, right? Okay? If you don't know how to draw Lewis structures, go back and review because we will now build off that. So we have to draw the correct Lewis structure first. And once we have that, we're going to look at the electron pairs around the central atom. Okay? So it's going to be important that you draw the correct structure. If you don't have the correct number of electron pairs around the central atom, you can't go on to this new model. Okay? And so this new model, let's scroll down a little bit. Again, here's your central atom that I just talked about. And we're going to count the electron pairs around the central atom. And it turns out we're going to count both bonding pairs and lone pairs, or what we also call non-bonding pairs. Okay, and I ran out of room, and when I do that, it scrolls up. Sorry about that. Okay, so we're going to count both bonding and non-bonding pairs of electrons because even though there's nothing bonded to a non-bonding pair on the central atom, it does occupy space, and we have to account for that. So the main premise of this theory is called Vsepr. Okay? And it stands for valence, shell. Okay? We know in the Lewis model we only count valence electrons, so we just focus on the outer electrons, the valence electrons. The core electrons are not involved in bonding. Okay? Electron, so Vse pair. Okay, we know the Lewis model is an electron pair model, right? And then the key to this theory is repulsion. So there's nothing new so far. We already knew that the Lewis model was a valence shell electron pair model. Now we're going to look at repulsions between the pairs around the central atom and how that will influence the shape or geometry, these all mean the same thing, or molecular structure of the molecule. All right, you may or may not have even thought about it, but the Lewis model doesn't really tell us anything about shape. All we've really looked at is how many pairs of electrons are around each atom, but we haven't said, well, how are those atoms arranged relative to each other? I mean, we draw a picture, but we really weren't concerned about how we connected things. Okay? So now we're going to actually start looking at what is the shape or geometry. How are the atoms arranged relative to each other? Okay, so we're going a step further past the Lewis model. Valence shell electron pair repulsion model. Okay, so this model was developed, I believe, in the 1950s by Gillespie and I can't remember the other guy's name. I should have looked it up beforehand. I remember Gillespie's name because I met him at a conference, I think in 1993. But essentially, this is kind of how science works. You know, there was the Lewis model out there that had been out there for a while. And then Gillespie says, well, let's go beyond that model. Yes, it's been developed. It's been shown to work in terms of accounting for where electrons are in most molecules. Remember, we talked about there are some limitations of the Lewis model. Odd electron structures in particular, but there's some other issues where you had to draw resonance and that and whatnot. So Gillespie builds on this. And so he says, well, what if we have two electron pairs around a central atom? Okay, so we're only focusing on the electron pairs around the central atom. So here's our two electron pairs. Let me scroll up just a little bit so you can see this. In beryllium dichloride. And I think it's obvious. You know, some of these structures are going to be really obvious. If we have two electron pairs, they're going to try to get as far apart as possible to minimize electron-pair repulsion. All right? Remember, again, this is valence shell electron-pair repulsion model. We're going to get the electron pairs as far apart. They're negatively charged. They're going to repel each other. That's going to determine our geometry or shape. Okay? So 2 electron pairs. And you do need to memorize this. 2 electron pairs around the central atom, linear. Okay? Now we're going to call this initially the electron pair geometry or electron pair arrangement, which might differ from the actual structure of the molecule. But 2 pairs linear. That's pretty easy. Okay? Now, this is where it gets a little bit tricky. This is not just 2 pairs of electrons, because a double bond, is a 4 electron bond. Okay, 2 pairs. So each of those is 4 electrons. But for the Vsepr model, okay, we're going to count double and triple bonds as 1 Vsepr pair. Okay? And the reason why we do that is even though a double bond is going to occupy a little bit more space than a single bond because it's more electrons, it's going to be focused in that same region of space between the nuclei for the most part. We'll talk more later about double bonds at the end of this chapter. But for the most part, it's going to be occupying roughly the same region of space as a single bond. So we're going to count it kind of as if it were just a single bond for Vsepr. So we would just count this as 1 Vsepr pair, 2 Vsepr pairs. We would say linear geometry, linear electron pair geometry. Okay, so we're going to count double bonds, triple bonds the same. What's kind of interesting is if you take 2 balloons and you tie them together, they will naturally adopt a linear arrangement. Okay, so you will see in the book it keeps showing these balloons, and it's because the balloons naturally, 2 balloons together will adopt a linear arrangement. When we get to 3, it will naturally adopt the arrangement that we can think of minimizing repulsion between the balloons. So there's our linear 2 pairs. What if we go to 3? Now, before we move on, I encourage you to build models. And you're going to like, but I don't want to buy a model kit. You can make a very cheap model kit by buying toothpicks and your favorite kind of sticky candy, okay, for lack of a better term. Something like gumdrops or dots. Or I've seen marshmallows. I don't think marshmallows work as good. I'm not going to even try to spell marshmallow, but you get the idea. I actually had a couple of students last year use, and I wouldn't recommend this, but they were trying to be healthy and not, eating candy so much, but they used cherry tomatoes. Maybe not the best. But basically you stick the toothpicks in to the gumdrops or whatever, and you stick other gumdrops on and you build yourself a cheap model kit. It actually works surprisingly well. So I would recommend that so that you can learn these shapes. So 2 pairs linear. What about 3? You might be thinking a T-shaped. If we did a T-shaped, we would have 2 90-degree angles and 1 180. Okay. It turns out that these short angles cause a lot of repulsion. So we want to try to minimize these smaller angles. So the best arrangement for 3 pairs is trigonal planar. Okay, and that's where we have these 120-degree angles. Okay, so all of these are going to be 120. All right, and so this is a molecule with boron in the center. We count 1, 2, 3 pairs of electrons around the central atom. Electron pair geometry, trigonal planar. Okay, so you're going to have to memorize. There's only 5 electron pair geometries you have to memorize. 2 pairs linear, 3 pairs trigonal planar. Now, again, to re-emphasize, sorry about that, I'm having trouble. I'm going to have to use my mouse to do this. I was trying to use my pen, and it doesn't work as well, as you can see. To re-emphasize, we're going to count a double bond just as 1, 2, 3. Okay, 3 pairs around the central atom, trigonal planar. Now, what you'll notice in this case, and you don't have to memorize bond angles, because on a quiz or something, you would just have to say the bond angles are 120, or approximately 120. They're not quite, okay, because, as you might expect, this double bond occupies more space than the single bond. Okay, no surprise there, because this is a 4-electron bond. So more electrons are going to spread out a little bit more, and it's going to push these hydrogens a little closer together. So these angles are slightly greater than 120, and of course, then this one must be compressed. Okay, so again, we're looking at if it's a perfectly symmetrical molecule like BF3. So let me just scroll back up just a little bit. Okay, we have boron with the same 3 atoms bonded, all single bonds. It's going to be 120-degree bond angles. But we can have differences depending on what's bonded. And in this case, since we have a carbon double bonded in oxygen, 2 hydrogens down here, we don't expect the bond angles to be exactly 120. So, 2 pairs linear, 3 pairs trigonal planar. You will be saying this in your sleep or waking up with a nightmare or something like that. So again, if we put 3 balloons together, tie 3 balloons together, they will they'll just adopt a trigonal planar arrangement. Okay? Again, we're maximizing the space between the balloons in this case. Linear, trigonal planar, you got that. Now, what about 4? And before I scroll down, you might be thinking, here's our central atom. Let me not use C because that would make you think it's carbon. Let's just use X. The obvious answer is that, oh, well, with 4, we're just going to make a square. And all of these would be 90 degrees. Okay? But the problem with that is we're still in 2 dimensions. We don't have to be stuck in 2 dimensions, do we? No. Let's move into 3 dimensions. We can get the electron pairs further apart. And that arrangement that gets the electron pairs further... Oh, sorry about that. I don't know where that one came from. That's like an extra. There we go. That arrangement that gets the electrons further apart is what's called a tetrahedral geometry, or a tetrahedron, as you can see the name down here. Now, why is it called a tetrahedron? If in your mind, again, we have a central atom somewhere in here, and then we have electron pairs going like this. If at the, where the outer atoms are, so say there's some atom A out here. If we in our mind, these A's aren't connected together here, but if in our mind we connected them in this kind of pyramid shape, the pyramid that we would make would have 4 sides. 1, 2, 3 on the back and 1 on the bottom. And 4, tetra. There you go. So tetrahedron. All the bond angles are 109.5. Now you do need to know these bond angles. Linear is easy, 180. Trigonal planar, 120. Tetrahedral, the normal tetrahedral bond angle is 109.5. So there are some things here you do have to memorize. Not too much though. So 2 pairs linear, 3 pairs trigonal planar, 4 pairs tetrahedral. Let's look at an example. So here would be the Lewis structure of methane. Or, as they say in Australia, we do have a chemistry professor at NAU that's from Australia. They don't say methane in Australia, they say methane, which kind of makes sense. It starts with M-E. Methane, methane. Okay, if we were to draw the correct Lewis structure for this, we'd count 8 electrons. Okay, and then we would put carbon in the center because hydrogen cannot be a central atom. We would make 4 bonds. Okay, and there's our 8 electrons. Structure is done. Okay, so for then the Vsepr model, we would count 1, 2, 3, 4 pairs around the central atom. The arrangement of 4 pairs that minimizes repulsion is tetrahedral. Okay, so you can see the Lewis model. We really don't worry about the arrangement. We actually drew this as what would be called a square plane. Okay, doesn't matter for the Lewis model because the Lewis model is not telling us the shape of the molecule. The actual shape of the molecule, we just have to then go from the Lewis model to the Vsepr model that says if there are 4 pairs around the central atom, the electron pair arrangement or geometry will be tetrahedral with 109.5 degree bond angles. And there's your tetrahedron. Now I think, I don't think I want to go to this next one yet, because this is 5 pairs. I want to go to a handout. Yeah, that's 5. Let's not do that yet. Let's come back to that later. So make sure you print out the handout right now that's in Sapling that says Vsepr handout. Okay, it'll be a PDF file. Print it out and follow along. Follow the bouncing pen or something like that. And so let me see if I got the right one. Yeah, here's part 1. So I'm going to do some of these very quickly because some of these were kind of in the notes already, but to show you how this works. Okay, so for beryllium, you can get, I don't want that. I'm going to have to pause here, sorry. All right, sorry about that, and I'm sure that didn't take very long, but I had to make sure that was an old document that I had already marked up. So BeH2, beryllium has 2 valence electrons. Each hydrogen has 1, so 2 for beryllium, 2 hydrogens each with 1. We have 4 valence electrons. Now, where did that go? Hold on. Okay. Guess I shouldn't work in Word, but this doesn't copy into OneNote very well, so surprisingly, Word documents don't copy into Microsoft OneNote. What a surprise. Okay, so beryllium has to be the central atom. We connect with single bonds. There's our 4 electrons. So for the Vsepr model, we would count 1, 2 electron pairs around the central atom. We would then scroll down to the next part of this handout and fill this in as you go along. I forgot, I've used electron-pair geometry, electron-pair arrangement. The book we're currently using actually, I believe, uses electron domain shape. Okay, we'll try to be consistent and use the same terminology, but again, that's the arrangement of the 2 electron pairs. That is linear. Now, if there are no lone pairs, okay, because we're going to talk about in a minute that lone pairs occupy space and we have to account for that. If there are no lone pairs, the shape or molecular geometry will be the same as your electron domain shape. Okay, you will see a difference. So this kind of seems obvious, but when there are lone pairs, the electron domain shape and the molecular shape won't be the same. And we'll get to that. Bond angles, linear, 180. That's it. Now, we'll do the rest of this on Thursday, most likely. Molecular polarity, hybrid orbitals, we'll do that later. So just stop filling out at bond angles. That's where we're going to stop. Okay, let's go up to the next one. Okay, so 2 pairs, linear. There you go. SO2, 6 electrons for sulfur, 2 oxygens each with 6, 18 electrons. Okay, connect with single bonds. Sulfur is less electronegative. It goes in the center. I'm going fairly quickly because we have drawn quite a few Lewis structures so far. That takes care of 16 electrons. I put 2 more on sulfur. That's 18. Are we done? No. Sulfur is short electrons. We can give sulfur more electrons by moving a lone pair up and making a double bond. And there's a better Lewis structure. Now, if you're thinking ahead like you should be, you should say, oh, but there should be a second resonance structure. And yes, there should be. Okay, I'm not going to draw it here because the second resonance structure is not going to change how we do Vsepr. And I also want to point out, and it might be in your book, it might not, there are some who would draw SO2 with actually 2 double bonds and have sulfur exceeding the octet rule with 10 electrons. Now, sulfur is in the 3rd row of the table. It can exceed the octet rule. There's a central atom. But why the heck would we do this? And it's because of formal charge. So you might want to assign formal charges for practice here and see why this second structure is better based on formal charge. Might be good practice. Now, from a Vsepr standpoint, it doesn't matter which of these two structures we draw. Generally, we draw, if we can, the structure that meets the octet rule. Okay, so for a quiz, I would say, go ahead and draw the first structure, because that one meets the octet rule, and that's kind of what the Lewis model is about. But for counting purposes, whether we look at this first structure or the second, we're going to count 1, 2, we count the lone pair, 3. So this molecule has it all. It has a double bond that we count as 1 for Vsepr, 1 pair. It has the lone pair, the non-bonding pair that we count as a pair, and then the single bond, 1, 2, 3. We would do the same thing with the second structure, 1, 2, 3. Okay, so it doesn't matter which one we draw as far as the Lewis model is concerned. Lewis model, the Vsepr model is concerned. Okay, okay, lots of stuff. So, 3 pairs, and this is what you have to memorize. What's the arrangement of 3 pairs that minimizes repulsion? And I can hear all of you right now. You're saying trigonal planar. So that is our electron domain shape. All right? So the first one, 2 pairs linear. Next one, 3 pairs trigonal planar. Okay? Now, here's where it gets a little tricky. And this is where building models really helps out to help you see what you have. Because there is a lone pair, all right, the molecular shape, in this case, will not be the same, will not be trigonal planar. Okay? So what will it be? Now this is where models help out. So I will bring models to class. So on Thursday, we will build some models. I would encourage you to bring dots and toothpicks or gumdrops and toothpicks or marshmallows and toothpicks and build models. I'm going to try to draw it as best I can here. These linear ones aren't so bad. So here we have sulfur. We have oxygen, oxygen, and there's our third part of the trigonal plane. This happens to be the lone pair. Now I haven't completed and put double bond and single bond because I'm just trying to draw how they're connected. All right? And so now what we're interested in for the molecular shape, we just want to know the arrangement of the sulfur and the 2 oxygens. How are the atoms arranged? Okay, the lone pair is up there occupying space. All right, and so how would you describe that arrangement? Well, that arrangement is quite often called V-shaped. Now, my V is upside down, but if you flip that over, you would see that it's the shape of a V. Also, quite often it is called bent because it's not linear. Okay, sometimes you'll even see it called angular. Okay, I think I prefer V-shaped. I think that describes it better. But again, any of those would suffice. All right, what about bond angle? Okay, what about bond angle? All right, so it's a trigonal plane. So this bond angle should be about 120. Okay. Approximately 120. Okay, it might be a little less than that because you have the lone pair that's going to occupy more space than the bonding pair and probably compress that bond angle a little bit. We also have a double bond there that's also larger, but again, it's going to be about 120. All right, so there's 2 pairs and 3 pairs. Now remember, if there are lone pairs like this structure, the molecular shape, the actual geometry, how are the atoms arranged, will not be the same as this electron domain shape. 2 pairs linear, 3 pairs trigonal planar. All right, now let's get to 4 pairs, I believe. Let's see if that's the case. Yes. Okay, so carbon tetrachloride. 4 for carbon, 4 chlorines each with 7. That gives us 32 electrons. Carbon goes in the center, it's less electronegative. Chlorines around the outside. Should have given myself a little more room on this document, but I hope you're following along okay. Complete the octets on the outer atoms first, then look at the central atom. If you look, all the octets are satisfied, and we have placed 32 electrons. So this is a good Lewis structure for carbon tetrachloride. Okay, so for the Vsepr model, count around the central atom. 1, 2, 3, 4. What arrangement of 4 pairs of electrons minimizes repulsion? And the answer is tetrahedral. Okay, let me get a blue pen here. I don't like to write in red too much except for highlighting. Okay, tetrahedral. Okay, now, because there are no lone pairs around the central atom, the molecular shape will be the same. That's easy. Now, the hard part here is, well, we can do the bond angles. Tetrahedral bond angle is 109.5 degrees. We'll draw out a tetrahedron in the next one. I'll try to show you how we tend to draw a tetrahedron in 2 dimensions, on a page to try to make it look 3-dimensional. It doesn't work particularly well, but you'll get the idea. But let's go to the next one. 5 electrons for nitrogen, 3 hydrogens each with 1. We have 8 valence electrons. Hydrogen can't be a central atom. We connect the 3 hydrogens. That's 6 electrons. Lone pair on nitrogen. There's your 8. Boom. There's your Lewis structure. So, counting. Again, we count the lone pairs. 1, 2, 3, and I can count 4. What arrangement of 4 pairs minimizes repulsion, according to the Vsepr model? 4 pairs, tetrahedral. Okay, so what I want you to notice, again, I'm going to repeat myself a lot, but I want to kind of ingrain this in. 2 pairs linear, 3 pairs trigonal planar, 4 pairs tetrahedral. It doesn't matter whether they're 4 bonding pairs, as in carbon tetrachloride, or 3 bonding pairs and 1 lone pair. It's 4 pairs, still tetrahedral. Oh, and there's my neighbor's dog. Okay, now, since there's a lone pair, the molecular shape, the arrangement of the nitrogen and the 3 hydrogens will not be tetrahedral. What will it be? And this is where models really help out. So one way that we can draw a tetrahedron is we kind of draw it with 1 bond up and kind of a tripod down. And so try to build a model right now where you have 4 toothpicks and you kind of have a tripod coming out the bottom. Now, what we try to do to try to emphasize 3 dimensions, and you don't always have to draw them like this, but if it's just a single line like I've shown here, that means it's in the plane of the page. If we draw a wedge that is solid, okay, that means it's coming out towards you. And then if we draw a dashed wedge, and I didn't draw this right because I did that okay. Kind of looks like a tripod down there. So hydrogen, 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 lone pair. Okay. What is now, how would we describe this arrangement of the nitrogen and the 3 hydrogens? Okay, how would we describe that arrangement? And this is where a model really works. And it's kind of hard to tell by my drawing here, but the nitrogen and the 3 hydrogens are not in the same plane. So let me go back to my notes and show you a picture from here. And I'm going to skip past 5 and 6 because we're not going to do those yet. Okay, molecules with lone pairs. So we've kind of talked about that. Lone pairs do occupy space, so we have to count them. Must count both lone pairs and bonding pairs. The shape of the molecule is the arrangement of the atoms. So even though the lone pairs are occupying space and influencing the molecular shape or geometry, we want to know just where the atoms are. And as I've mentioned, build models. Build models. Okay, so that's just trying to show you lone pairs occupy more space. Not that big a deal because it's only attracted between 1 nuclei. So here we go. Here's ammonia, NH3. Okay, here's our 4 electron pairs. Okay, 3 of these are bonding. So here's our tetrahedron. 3 are bonding, as we just saw. Sorry. Here's our lone pair occupying space. In fact, it occupies more space in the bonding pair and compresses that bond angle from the normal tetrahedron of 109 down to 107. Again, you don't have to memorize that bond angle, but you should understand why that bond angle is slightly less than 109. It's because this lone pair occupies more space. So how would we describe this arrangement here? Okay, and I didn't go through my slides enough, but I think I have a better picture next, I hope. Okay, so that's the actual molecular geometry. Okay, And here's how we describe it. So the electron geometry or the electron domain shape, I'm going to look in your book and see which one it is. I think they used to use electron geometry in this book, but with the new edition they use electron domain or vice versa. I can't remember which one. But a lot of you have the old edition. So maybe we'll talk about in class what we want to use to talk about the electron shape, tetrahedral, 4 pairs. The molecular geometry, it's actually a pyramid because the hydrogens are actually not in the same plane as the nitrogen. And if we connect all of these, we kind of get a pyramid shape. It's kind of hard to see, but we get kind of a pyramid shape. So it's still trigonal in the sense we have 3 hydrogens, but they're not in the same plane. The nitrogen's above the plane of the hydrogens. So we're going to call that a trigonal pyramid. Okay, and I don't know if I have another picture that might show this better. No, but build models. Water comes next. So water's a little easier to see. But build a model, build a tetrahedron. Okay, so build a tetrahedron that looks something like this with 4 toothpicks. And then here's your lone pair on top. Pull that toothpick out and see what you're left with. And you'll see that the nitrogen's not in the same plane as the hydrogens in this case. And the best way to describe this is if we, in our mind, let me get a different color here. If in our mind we connect all of these, now the hydrogens are not connected, but if we connect all those, we end up with a pyramid with a triangular base, or what we also call a trigonal base. So that's a trigonal pyramid. Okay, so this is a little tricky. The basic shapes are easy, but then building models really helps when you move past the basic shapes and start having lone pairs. What do you end up with? Sorry, I got a little choked up there. Okay, let's go back to our handout. Oh, not that handout. That's the next one. I don't know if we're going to get to that in this recording. We'll see. So, because we have this lone pair, the molecular shape, you don't have to draw it. I don't want you to draw it. Just give me the name. And the name is trigonal pyramid, or trigonal pyramidal, or you can say pyramidal, whichever you prefer. I actually prefer pyramidal, but trigonal pyramidal, trigonal pyramidal. And what are the bond angles? Normal tetrahedral bond angle, approximately 109. And we showed in that thing that it's actually slightly less. Sorry, I can write 107 down here because this lone pair occupies more space than a bonding pair. All right. Fun stuff. I like Vsepr. I like the Lewis model too. It's just that the Vsepr builds on the Lewis model. Last one on this handout, water. 6 electrons for oxygen, 2 hydrogens each with 1. We again have 8 valence electrons. Hydrogen cannot be in the center. Connect with single bonds, 2 lone pairs on oxygen. Check, there's our 8 electrons. Octet is satisfied for oxygen. Each hydrogen has 2. That's all it can have. We're done. Now, I would like to point out here that the way I drew this, and again, the Lewis structure doesn't matter how you arrange them. We just want to find out where the electrons are at this point. I drew water as linear. But is it linear? Is it linear? Well, let's find out. 1, 2, 3, 4. So 4 pairs for Vsepr, 2 lone pairs, 2 bonding pairs. What's the arrangement of 4 pairs of electrons that minimizes repulsion? And I hope you're saying it, tetrahedral. So that's the electron pair geometry or electron domain shape. What about the molecular shape? Well, it's not going to be the same because we have lone pairs. Okay, so we just want to know how are the 2 hydrogens and oxygen arranged relative to each other. So again, this is where building models. Build yourself a tetrahedron with 4 toothpicks. Get that kind of tetrahedral shape with 1 pair pointing up and a tripod pointing down, and pull 2 toothpicks off and see what you're left with. I'm going to try to draw it as best as I can here. Oxygen. And I'm not going to put forward and back, but let's just do, okay, there's our tripod. All right, so let's just put it, kind of doesn't matter. Sometimes it's kind of easier to see. Let me put my 2 lone pairs here on those. Turns out all positions in a tetrahedron are equivalent, so in 2 dimensions they don't look equivalent. trying to draw it in 2 dimensions, but in reality there are. So look at your structure. That if you build a tetrahedron correctly, all 4 positions are equivalent. And then if you look at this bond angle here, I hate when I hit a certain button and that true suite pops up. I don't even know what it is. I don't think I've ever used it. But it pops up at an inopportune time. So you can see that's not linear. It's not linear. So what would it be? Well, look back at SO2. How do we describe a nonlinear shape? Well, we would describe it as V-shaped. Okay. We might describe it as bent. Something to indicate that it's not linear. All right. Now, here's where it gets tricky. What would the bond angle be? What would the bond angle be? Well, remember we're building off of a tetrahedron. For SO2, which ended up with a V-shaped or bent shape, we were building off a trigonal plane, which has angles of 120. For water, we're not building off a trigonal plane. We're building off a tetrahedron. So it's going to be close to the tetrahedral bond angle of 109. Okay? Now, will it be exactly 109, or what's your prediction based on having 2 lone pairs? Lone pairs occupy more space than bonding pairs, right? So we expect that bond angle to be compressed. 1 lone pair compressed it to 107 in ammonia. 2 lone pairs in water, probably going to compress it a little bit more. Okay? You don't have to know what the value is, but you need to understand why. And if we go back to our notes here, and I will post these lecture notes in Sapling, Chapter 10 lecture notes, these will be there. You can go back through this material as well. There is our electron geometry, tetrahedral, 4 pairs, 1, 2, 3, there's the other bond, 4. 4 pairs tetrahedral, but since we have 2 lone pairs, the geometry, the molecular geometry, or what we also call the shape of the molecule, will not be tetrahedral. And as we talked about, you can see the arrangement here, certainly not linear. It's going to be V-shaped or bent. Okay, so your book is using the term bent. I tend to like V-shaped a little bit better. Doesn't matter, I'll accept either. And hopefully it's going to show us the bond angle here. There we go. Trying to show with these kind of highlights here that lone pairs occupy more space. It's going to push these 2 bonds closer together. And look at that, it pushed it together by about a 5-degree difference from 109 down to 104. Okay, again, you don't have to memorize that 104.5 degree number, but understand why it's less than your traditional tetrahedral bond angle of 109. Okay, let's see where that takes us. I'm about 40 minutes in, I think. I do want to go about an hour. I don't want to go an hour and 15 minutes. Our lecture's an hour and 15 minutes. I think an hour will be enough, so we have about 15 minutes. Let me just pause here real quick. You don't need to know I'm pausing. I want to get rid of this authentic true suite, which I have never used. Don't know why it's on my computer. Oh, okay, so I've gone 38 minutes. Okay, so let's go about another 20 minutes. So we've pretty much gotten through, on this handout, 2, 3, and 4 pairs. Okay, 2 pairs linear, 3 pairs trigonal planar, 4 pairs tetrahedral. Now you do have to do more work past that depending on if you have lone pairs. You know, this first one, no lone pairs, linear, linear. This one here, tetrahedral, tetrahedral, no lone pairs. But it's more work figuring out the shape of the molecule if you have lone pairs, and that's where building models really helps. All right, so let's go back to our notes for 5 and 6 pairs. Scroll back up here. Okay, so what is the arrangement? There was tetrahedron. Okay, this is what I want. Sorry for jumping around there. What arrangement of 5 pairs of electrons minimizes repulsion? And it turns out it's what's called a trigonal bipyramid. Okay, so we have a trigonal plane, which is shown by these. Oh, red's not good with a red balloon, is it? These 3 balloons, okay, 3 balloons together in the same plane. It's going to adopt that trigonal planar arrangement. Okay, so we've seen that. But now we have to put a 4th and a 5th balloon in, 4th and 5th electron pair, and they're going to arrange themselves above and below that trigonal plane. Okay, so again we have the trigonal for this trigonal plane, and then bipyramid, where the heck do they get these names? Well, if in your mind, so let me just say, here's our central atom. There's our trigonal plane. One pair below, one pair above. Now, again, you have to use your imagination here. If you connect all of these, there's your trigonal base. I hate when that happens. There's your trigonal base to the pyramid. Okay. That was interesting how that happened. And then, don't look at that red line, but if we connect up, now these are not connected, but again, you have to use your imagination, and I didn't draw that right. Gosh, I hate that. Oh, and I don't, I have to figure out where one note hid their eraser. If you connect all of these above and below, and my drawing's awful here, as you can see, but there's a pyramid above and a pyramid below. There is your bipyramid. Okay, so trigonal in the middle, and then a pyramid above, pyramid below. Have to use your imagination, because these things really aren't connected like this, but that's how we get these names. Okay, and bond angles. Let's see if the bond angles are shown better on the next slide. Yeah, let's do this. So trigonal plane, this should not surprise you. We talked about a trigonal planar bond angle of 120. Pair going up, pair going down. Clearly there is a 90-degree angle, both of those there. All right. Just a little bit more terminology. We will talk about these being the trigonal planar positions, which is one way to describe it. But we can also use the terminology in terms of, say, a globe or the Earth. Around the center we have the equator. So these ones in the trigonal plane are called the equatorial positions. And then the axis, say the axis of the Earth, up and down, we call the positions up and down the axial positions. All right, so you do need to know that terminology, because if I say, oh, those are the equatorial positions, those are the axial positions, you'll know what I mean. Okay, so here's PCl5. 1, 2, 3, 4, 5. Phosphorus exceeding the octet rule. The electron geometry is going to be trigonal bipyramidal. And because there are no lone pairs, so this is the electron arrangement or electron geometry, is trigonal bipyramidal. The molecular shape will be the same. It's also trigonal bipyramidal because there are no lone pairs. All right, there you go. And then the last shape you need to know. So 2, 3, 4, we know those. Linear, trigonal, planar, tetrahedral. 5 pairs around the central atom, trigonal bipyramidal. And 6 pairs. How are we going to arrange those? All right, pretty similar. We're going to have, instead of 3 in the plane, like a trigonal bipyramid, we're going to have 4 in the plane. And you can't quite see those, but we're going to have a square plane in the middle, and then we're going to have 1 up and 1 down. Okay? And you're probably going, where did this name come from? Octahedral. Well, we do the same thing. We connect them all and create this bipyramid again with a square base. So you might be thinking, why don't we just call it, instead we have a trigonal bipyramid, why don't we just call this a square bipyramid? I guess we could, but that's not typically what it's called. It's called octahedron or octahedral 8. Well, where does the 8 come from? Well, it comes from 8 faces of our bipyramid. 2, there's 3 in the back, 4 in the back, okay? And there's 5, this front one, 6 in the front. Now go to the back, 7 back here, 8 over here, kind of in the back side. There are 8 faces of that square bipyramid. 8 faces, octa, okay? Octahedral. There you go. Okay, you do need to know those names. 2 pairs linear, 3 pairs trigonal planar. I know you hate me saying it again. 4 pairs tetrahedral, 5 pairs trigonal bipyramidal, 6 pairs octahedral. There you go. And I think there's an example shown here. SF6. I think we've drawn the Lewis structure for SF6 already, so look in your notes. And sulfur does exceed the octet rule, but we count 1, 2, 3, 4, 5, 6. The arrangement of 6 electron pairs that minimize repulsion is octahedral. And since there are no lone pairs, the molecular shape will be octahedral as well. All right. What about bond angles? All the angles, whether we're in the square plane or axial to equatorial, they're all 90. This is a highly symmetrical. All 6 positions are equivalent. Octahedron, 90-degree angles. All right, let's, I don't think I have more with those right now. Let's see. Here you probably can't see this. Print out your notes. This summarizes the 5 basic shapes: linear, trigonal, planar, tetrahedral, trigonal bipyramid, octahedral. We've gone through that. We've talked about molecules with lone pairs already. I'm going to scroll down. Let's see if I just want to make sure I get through enough notes. I do want to get back and do a few more problems in the handout. Okay, we'll come back to this because we've done these 3. We actually on the handout did carbon tetrachloride, but it works out the same. But this is a nice slide to sum up the previous handout, where we did, gosh, I'm having trouble getting this to scroll right. The effect of lone pairs on geometry. So all of these are tetrahedral. Let's use domain shape. I think that's what the book is using. Tetrahedral electron domain shape. All right? But methane, in this case, doesn't have any lone pairs, so its molecular shape is also tetrahedral. Okay, so its molecular shape is tetrahedral. Okay, ammonia has 1 lone pair. Its molecular shape is a trigonal, not bipyramid. This is just a single pyramid. Okay, here's your trigonal base at the bottom, and nitrogen is above. There's your trigonal pyramid. And water with 2 lone pairs on the central atom is going to be V-shaped or bent. Okay, and this also shows the effect on the bond angle of having lone pairs. Nice slide. Okay, I don't think I want to go to the next because the next one is 5 pairs with a lone pair. So let's go back. This is also there with the handout, so they're both there. So the Vsepr handouts, both sheets are there. Let's go through very quickly. We just did, I think it was PF5, right? Or was it PCL5? I don't think it really matters. What did we just do up here? PCL5. Okay. We're going to find the same thing. It shouldn't surprise you. Replace chlorine with fluorine. So for this one, I'm not going to complete this. I think you can do this. Oh, I'm sorry. I have markup on all this again. I'll have to pause here for just a second. Hang on. I forget that I use these over and over again. That gives me a chance. All right, I'm back. Did you miss me? Sorry about that. Hopefully things are working out okay here. Let me make sure I have volume. Check, check. Oh, I do have volume. Good. Okay. I was worried because my microphone didn't look like it was working right. So, sorry about the confusion there. See if you can draw this so that you end up with phosphorus with 5 bonds to fluorines. Okay. With all the octets on fluorine satisfied. So make sure you can draw that correct Lewis structure. It will look just like PCl5 that we just saw. The electron domain shape, 5 pairs. That'll be a trigonal bipyramid. Since there are no lone pairs, the molecular shape will also be a trigonal bipyramid. Okay, and the bond angles, there's 2 of them, 120 and 90. 120 in the plane, 90 between axial and equatorial. I'm sorry about that. I don't have it set to the right. I want final. There we go. Okay, so practice that one. It's going to look just like PCl5 that we just had in the notes. So for sake of time, we only have about 10 minutes. I want to get to the next couple. SF4. Let's go ahead and do the Lewis structure for this. 6 valence electrons for sulfur, 4 fluorines each with 7. That gives us 34 electrons. Fluorine is the most electronegative. Oh my gosh, where did that go? Okay. I'm probably going to draw it there. It's going to come back. That's interesting. Now, again, how we draw our structure. You know, when we have 4 bonds, You know, we're probably going to default to a square plane because that kind of seems what 4 bonds should be. Doesn't matter for drawing a Lewis structure. We don't have to draw the correct shape of the molecule. We just want to know where the electrons are. Okay, so single bonds. We complete the octets on all the atoms, outer atoms first. We now have placed 32 electrons. We have 2 more electrons to go. Where do they go? If we have extra electrons, we put them as lone pairs in the central atom. All right, so for Vsepr, what are we going to count? 1, 2, counting the lone pair, 3, 4, 5. What's the arrangement of 5 pairs of electrons that minimizes repulsion? Sorry about that. Trigonal Bipyramid. All right, now I'm going to try to draw it. Now again, in this box I want you to write the name, but I'm going to draw it as best I can. So I'm going to draw a trigonal bipyramid. Okay? One of these is a lone pair. Lone pairs will always go in the trigonal plane. There's more space there, trust me. There's more space in the trigonal plane. 120 gives it more room to spread out. So here's our 4 fluorines. Okay? So a lot of students like to default and say, well, it's 4 bonds, it's tetrahedral. Well, you can see how this is drawn, that it's not tetrahedral. Okay? So quite often, since there are 4 bonds here, so 4 fluorines, we will call this a distorted tetrahedron. Okay, or a distorted tetrahedral structure, so that's what you should write there. Let me show you, go back to the notes and show you this in the notes so you can get a feel for the other name that's used for this, if I can find it. I know it's here somewhere. It would let me get to where I want to go. I'm not sure why the scroll function on this. Okay, there we go. So here's a nice slide because it points out a couple of things. There's more repulsion if we put the lone pair in an axial position, so it doesn't go there. Lone pairs in a trigonal bipyramid structure will always go in the equatorial plane. All right. So what does that leave us? Well, you can see another name. Distorted tetrahedron is fine. 4 bonds. Not tetrahedron, of course, but let's call it distorted tetrahedron. But it's also called a seesaw. Now, build a model, and maybe you'll be able to see this, but we'd have to rotate it down so that these two form the base of the seesaw. Okay, so these two angled, if we rotate them down, I'll build a model and show you in class this seesaw shape. Put those down, and then these 2 fluorines would be the part of the seesaw or the teeter-tot or whatever you call it. They go back and forth. Again, for these shapes, you have to use your imagination. So distorted tetrahedron or seesaw. Okay. And what about bond angles? We still have approximately 120 in the plane, and we still have 90. All right, so if we go back, and I don't think we have more on this slide that's related to this molecule. Let me just double check before I move back. Nope, that's the next molecule. Okay. So bond angles are still going to be about 120 and 90. All right. In the last few minutes that I have, maybe we'll just do this last structure because I really don't want to push you guys past 60 minutes. I have 6 more minutes. Okay, I3 minus. We have 3 fluorines, each with 7, 1 for the negative charge, 22 electrons. What goes in the center? Oh, trick question. They're all iodine. Okay, iodine goes in the center. Complete the octets on the outer ones first. That's only 16 electrons. We have 22. Complete the octet on the central iodine. That's 20. Okay. We have 22. If we have extra electrons, where do they go? They go as a lone pair on the central atom. That's why I left myself some space there. Okay. Now, we should either assign formal charges at this point because we have a negative charge to show that, but we'll just put square brackets and put our negative charge there. Not worry about assigning formal charges right now. All right, Vsepr. There's a Lewis model. I drew it linear. Is it linear? Maybe. Let's see. 1, 2. We count the lone pairs. 3 for the bonding pair. There's another lone pair. 4, 5. 5 pairs. 3 lone pairs, 2 bonding pairs. What's the arrangement of 5 pairs of electrons that minimizes repulsion? The answer is Trigonal Bipyramid. But since we have lone pairs, the molecular shape or molecular geometry will not be a trigonal bipyramid. Let's put our iodine, let's draw our trigonal bipyramid. And again, I want a name here, not the shape, but again, I'm trying to help us get to this shape. There's our 5 pairs around the central iodine. Lone pairs in the trigonal bipyramid will always go where? In the trigonal plane, in the equatorial positions. So we're going to put all 3 in the equatorial positions, the trigonal plane. We're going to put the iodines in the axial position. And what shape do we end up with? I, down the middle, we end up with a linear shape, molecular geometry. It's kind of hard to see. My bonds and my iodines kind of blended together. So let me highlight. That's kind of funny, isn't it? Okay, there's my 3 iodines in a straight line. It's a linear. Now this is where you got to be careful because our bond angles, our normal trigonal bipyramidal bond angles have gone away, right? They're normally 120 and 90, but we end up with a linear shape. Well, the angle for a linear shape is what? 180. Be careful. That's a little tricky because it's like, oh, trigonal bipyramid, it's 120 and 90. But if we start putting lone pairs everywhere, the bond angle is where are the iodines arranged to each other, and they're arranged in a line, 180 degrees. All right, let's go back to our notes. I might save this last spot for class on Thursday. Let me show you a few more things with the trigonal bipyramid. Here's another molecule you might practice. Practice BRF3 and see if you get that Lewis structure. Okay, now turns out that this is actually drawn in the right geometry, but it doesn't have to be. But again, we would do the same thing. We would count 1, 2, 3, 4, 5. What's the arrangement of 5 pairs that minimizes repulsion? Trigonal bipyramidal. All right. The 2 lone pairs are going to go in the equatorial positions, the trigonal plane. And what does that leave us? Well, we have an axial one pointing up, axial pointing down. We have 1 left in the trigonal plane. What is that shape? Well, it's kind of, you kind of have to rotate at 90 degrees to see, but we're going to call that a T shape. So, rotate this 90 degrees, and you'll see that that's a T-shaped arrangement. So some of these names for the molecular shape make sense. This one is called a T-shaped. So again, if you have lone pairs, trigonal bipyramid, they go where? Trigonal plane. 1 pair, 2 pairs, 3 pairs, doesn't matter, always in the trigonal plane. And then, since we have lone pairs, our molecular geometry is not the same, and it's going to end up being T-shaped. Bond angles. Again, we've kind of messed up the bond angles. We still have the 90-degree equatorial to axial, but now our trigonal plane angle's gone away, and we actually now have a 180 here again. So we've gone to 90 and 180 on this molecule. So again, building models helps you see these bond angles as well. Okay, lots of visual stuff going on here, visual in 3 dimensions. Here's very similar. This xenon difluoride is very similar to I3- that we just drew. Okay, we would say these are isoelectronic molecules. Okay, so compare these two. 5 pairs, trigonal bipyramidal electron-pair geometry. All 3 lone pairs go in the trigonal plane. What are we left with? Linear. We just saw that. All right, I think I've done enough for this lecture. I think I'm up to the point where we're to octahedral. Let's save that for class on Thursday. I do have a few things to clear up in. I thought my timer was paused. Look at that. I'm going to get right at an hour. Perfect timing. going to clear up a few things in Chapter 9, difference between ionic and covalent bonding, a little bit more with bond energy. So we'll do a little bit with Chapter 9 on Thursday, and then we'll jump into Vsepr. I'll ask if there's any questions on what I've gone through in this lecture, and then we'll do octahedron, and that will get us through Vsepr, and then we'll start looking at something called molecular polarity, and then given enough time, we will get into hybrid orbitals. Okay, so thanks for being patient with me. Thanks for sitting through this. It does help since you never know where Veterans Day is going to fall and what day of the week gets canceled because of classes. So it's hard to plan. So having this recording definitely helps us to stay on track to cover what we need to for the semester. And you might be saying, well, can't we just do what we get done? Well, the problem with that is this is a multi-section course. We're one of a number of sections of Chem 151, and we all take a common final. So I do have to make sure you guys have the material that will prepare you for the final exam. Okay, thanks for sticking with me. An hour and 1 minute. Sorry about that. I will see you in class on Thursday. Enjoy the holiday.